Okay. One question for you guys. There were a few people who had mentioned they were having trouble finding class lecture recordings. Did those all get resolved? Are you guys finding everything? Is there anything missing that we need to get up? Was there a recording of last Thursday's lecture? There should have been.
So I found out that the lecture recordings aren't made available automatically. There's an extra step I have to do, and press a switch.
Okay. All right. So will last Thursday's be made? It is up now. Okay.
It is. Yeah, it's up now.
Okay. So I apologize for that. We'll make sure that those are up a little bit sooner. They should have been going automatically, but just a little thing that we missed. So okay. So let me share my screen. When will week 2? They should be up now. Week 2 readings should be up now. Thanks for asking, Kate. Are they up, Yoon?
They're up.
Yeah, week 2 and 3 readings should be up now. And there's some information on the history of toxicology, recapping from kind of the initial lecture. And then there's a contaminant amplification in the environment paper. And we're going to get into that today. So if after class today you have time, I would highly recommend looking at that paper right after class, because it will make a lot more sense than before. Although everybody's different, some people like it first, but I think for that content, you'll like it better after class. Okay, so share screen, share, and can you guys see the slides? Okay. All right, so I just want to recap a little bit, finish up some stuff from last time. Feel free to put questions in the chat. I'm going to pull that up here. Where we left off. Okay, so let me back up one slide and basically remind you of what we were talking about. So we said what a bioconcentration factor, sometimes also called the bioaccumulation factor, is the concentration in an animal versus the concentration in the environment. Some of you indicated interest in marine mammals, and part of the reason why marine mammals are such a big deal and why people are so interested in marine mammals is the bioaccumulation factors are massive, massive. So in this case, if you take a beluga, for example, the bioconcentration of polychlorinated biphenyl, let's say 180, which is the highest one on that list, is 11.7 on a log scale. So that's really, really high. That means the concentration in the animal is many, many, many times higher than the concentration in the environment. So the question I left you with, and that you thought about all weekend, was, is a compound that has a bioconcentration factor that's 10 to the 12th, is that at equilibrium, right? Because our whole principle, the whole principle of the chemodynamics, the reading from Don Crosby on chemodynamics, the whole principle of that is chemicals are always trying to come into equilibrium in the environment. And so at some point they come into some equilibrium. So you take something like DDT or PCB, those are chemicals that have largely been phased out. So why are they so high in a whale? Why are they not in equilibrium? And is that just a hydrophobicity issue? And what I said to you is that doesn't make sense, because if it was just a fat issue, if you took a piece of fat from a whale, it would be the same as a piece of fat from a sardine, as a piece of fat from a salmon, as from anything else. And the answer is no, it isn't. So you can begin to put some life history explanations into that. You can say, well, the whale lives a little bit longer, but then there are some very long-lived bony fish that don't have high levels. So you can't get there simply by equilibrium. Okay, so how do we figure this out? And so recall our definition of solubility in water. It requires some molecular polarity. Is DDT polar like sodium chloride, right? That's the question I'm going to ask you. Is there a polar group on DDT? No, there isn't. It's completely neutral, right? So for many organic compounds, a better way to understand their behavior is to understand their solubility in lipids rather than their solubility in water. And you can take octanol, which you can think of as basically like water is a solvent for hydrophilic compounds. Octanol is a solvent for lipophilic compounds. And you can estimate solubility in fat by measuring solubility in octanol. So you can look at a substance and say, if it dissolves in octanol really well, it's probably also going to dissolve in fat really well. Okay, so how do you do that? Okay, well, like let's just say for many compounds, you know, what you want to do is know the relative solubility in octanol versus the relative solubility in water. And that's called the octanol water partition coefficient. And it's written KOW. And DDT, for example, has a log KOW of about 5 or an absolute KOW of about 100,000. And so what you can do is imagine that the stuff on the top, the red stuff is octanol, and the stuff on the bottom is water. You can take your toxin, in this case DDT or whatever, and you can put it in this separatory funnel, and you can shake it around, shake it, and mix it for a day or two, and then at some point let the organic phase and the aqueous phase separate, and then measure experimentally how much is left of your DDT in the water and how much is in the octanol, and that's the octanol water partition coefficient. Okay, so it can be measured experimentally, but most octanol water partition coefficient data that are present in the literature are estimated from computer simulations. And the reason that this is so important is that you can actually predict bioconcentration factors from octanol water partition coefficients. I'm showing you a graph, and this is directly from one of the readings, from the Crosby reading. Basically, if you look at the log of the octanol water partition coefficient on the x-axis and the log of the bioconcentration factor, those two are basically related. And the reason, of course, is that tissues are the major lipid compartments in nature. So if you treat yourself as a compartment, basically things will partition into lipids, and you get this nice correlation. So one way to put this is octanol water partition coefficient is the 800-pound gorilla of predictive tools for understanding accumulation in organisms, because it's directly proportional to the bioconcentration factor. And what I want to tell you is it doesn't always work. And sometimes octanol water partition coefficient doesn't actually predict the behavior of chemicals. And we're going to go deeper into that in subsequent lectures and really talk about that and why it does. Okay, so let me stop that. Any questions so far? Everybody with me thus far? Anything, everybody following? Anybody look at the Don Crosby reading yet? So I see a thumbs up from at least a couple people on that. Does anyone want to kind of weigh in with the Crosby reading? How is that? You guys like it? Is it clear? Covering a lot of the same ideas? Anybody dislike it? Okay, so let's move forward now to today's content. Okay, that way. All right, so, okay, so the reading on TED that has to do with what we're going to talk about today is contaminant amplification in the environment. I'll encourage you guys to look at that. So I want to recap what we've covered so far from last week. What are chemodynamics? All right, so if you're reading this in Crosby and you're getting confused, I want to make sure that it's clear for you. It describes the movement of chemicals in the environment, and it's important because it can be used to predict where they'll end up. You can predict right now where some of these oil hydrocarbons are going to end up in say, fish from Southern California. It involves properties of chemicals and the environment. There are constants that govern movement, Henry's constants, KOC, KOW, and there are properties of the environment that govern chemical behavior. And that's a really important thing to recognize. pH, salinity, wind, and ocean currents. That's being illustrated to us very clearly right now as we sit here and we wait to find out if that oil slick is coming here. And there are also behaviors of chemicals in the environment that govern partitioning. So these interact with the properties of chemicals. If a chemical has a high Henry's constant, it will evaporate in the tropics and may condense at the poles. And we talked about those: dispersion, advection, atmospheric ocean transport, and biotransport. So, okay, but what do we really want to know, right? Like, what is it? This is like an environmental health class. So what are we really asking? We're really asking, is the chemical or the pollutant going to end up in me or in you or in some animal that we're interested, or plant that we're interested in studying? And so, if we ask ourselves, how does that work? We really need to understand bioaccumulation. So what is bioaccumulation? And remember, we broke it down and we said there are some definitions for the class. And I think someone, I'm sorry, I might have been Catherine actually, but anyway, said, I've had some of these definitions before. So I made a point of really, oh, sorry, I missed something in the chat. Madhu, you had asked about explaining the last two examples. Are those the ones that don't bioaccumulate? Well,
yeah, those examples.
Oh, thank you. Okay, I will go into those more. Okay, sorry I missed that, and I will go into those more later on. And if I don't, please ping me again. I'll make sure those are crystal clear. So I know I skimmed over those because I'm going to get into them in greater depth. We're actually going to draw those out and really make those clear. Okay. All right. So there were some definitions that we put up, and we said, look, if you've looked at this before in another class, they may have used them differently. And for this class, it's really important to clarify what you mean by bioconcentration, biomagnification, and bioaccumulation. So bioconcentration, passive movement, right? There's oil in the water, there's fish in the water. The oil likes to be in lipid. So some molecules from the crude oil, it's a huge mixture of different molecules. Some molecules are just going to passively diffuse into fish, right? Then there's biomagnification, which is this idea that you might have basically like a small fish, like an anchovy or something, that gets eaten by a calico bass, a larger fish. And as you go up the food chain, you're going to get a higher and higher level. And biomagnification is a little bit odd because you expect at some point the compound will come into equilibrium. So it shouldn't be a continuum to infinity, right? Because at some point, lipid is lipid, it's going to come into some equilibrium. And bioaccumulation, which is the sum of the two, is the thing that we really observe. So we go out and we get a piece of little stab of whale blubber and we look at it and we go, wow, that's pretty high in these, and that's bioaccumulation. That's what we're actually observing. So we talked about, how do we do this? What if we measure pollutant level directly? How much DDT or other pollutant gets into an animal? And so we said, there are these three steps. Basically, you go and you get the animal or some tissue from the animal, you grind it up and you do the mass spec, and then you get these very high concentration levels that are millions, hundreds of millions of times, or billions of times greater than the levels in the environment. So how does that all work? And we talked about the solubility definition and the octanol water partition coefficient. So let's come back to this kind of trick question. Why is fugacity preferable to concentration? And at equilibrium, fugacity in fish equals fugacity in water. In other words, the partial pressure of a compound at equilibrium is equal in both compartments. However, the concentration is very, very different. So you can have 1,000 times more in the fish than in the water, and there's no partial pressure. So at equilibrium, the fugacity in fish and the fugacity in water might look like this, and the units are pascals, even though the concentrations denoted by C below are so different. Okay, so tissues are the major lipid compartments in nature, and octanol water partition coefficient and bioconcentration factor are directly related, right? And so we have these examples of things that don't behave, and I'm still gonna I'm not gonna spend too much time on those, but we know that sometimes they're out of equilibrium. So in nature, many systems appear to be out of chemodynamic equilibrium. And what's actually going on is biomagnification at a scale that looks like really striking. So how can we explain this with our understanding of fugacity and pressure and concentration? So let's take an example here. And the example we take is, there's some compound from this oil spill that's present at low concentrations in the water. It has a very high fugacity. And then it goes into a fish, right? And it has the same fugacity. So it's at equilibrium. That's bioconcentration. Nothing out of the ordinary happens. But what happens? What happens? Now let me ask you a different question. What happens when a hammerhead shark eats that animal and now has a concentration of 10,000? What do you guys predict the fugacity is there? Do you think it's still 500? Jack says 500. Okay, so it turns out, and that's this week's reading, it turns out it isn't. So this week, basically, you have a reading that deals with this problem. And the reading is called Contaminant Amplification in the Environment. I really like the use of the word amplification here because it really captures what's going on, right? You're not just increasing, it's not just accumulation, it's actually amplification. You're actually increasing the relative concentration at upper food levels in a way that you wouldn't predict. And remember, I actually took a class from Don Crosby, and Don Crosby would say, there's no way, right? Biomagnification is wrong. It can't work. Lipid in a fish is the same as lipid in a bird. So it just comes into equilibrium and then it's there. And then you'd say, well, yeah, Don, that's great. Based on chemodynamics, that's correct. But if you go in the environment and you measure a whale, it's a lot higher than that. And so what's going on? And so this has been a big debate in the field. There isn't, by the way, this, nobody really knows. So I should say, like, take McKay's example as one idea, but it's one that I find really satisfying, one that I find really good. So Don McKay basically gives us this analogy in the paper. It's a really, really important analogy. And I want you guys to kind of follow along with me in this analogy for a second. So Don McKay says, okay, so the first picture, you've got basically a scientist, right? That's your depiction of a scientist. And your scientist is working in the lab, and he's a chemist, and he wants to measure the level of DDT in seawater. So if you went out and you got seawater, you just got a bucket of seawater and you measured DDT in it, it wouldn't work because the level's too low and your instrument's not that sensitive. So you wouldn't be able to measure it, right? This too low. So what do? Okay, well, you go from, based on the lecture, and you go get the separatory funnel, you put some octanol in it, and you shake it, and you extract the seawater and solve it. And now you have more, but it's still too low. It's still not high enough. So what can you do next? Well, and I apologize that this is actually condensing that I'm showing you, but envision that you now have the solvent here and you're evaporating off the solvent and you're concentrating down the extracted stuff by evaporating off the solvent. Oh, by the way, you're wondering why I've used that picture, and I just want to point out this is kind of the skew in our society. So if you type in rational scientist, you get 6 million, 7 million results. You type in crazy scientist, you get 9.6 million. So it's like pretty interesting. Okay, so what's happening to fugacity and concentration as the chemist concentrates the seawater? So let's do a graph, and on the x-axis of the graph you have fugacity, and on the y-axis you have the concentration. So let's take the first step of this graph, right? You have a concentration of 5 micropascals, right? A fugacity of 5 micropascals and a concentration of 1 nanogram per liter of your DDT, right? And as you move from the water into the bioconcentration step, basically there's no input of energy. It's just a passive movement based on lipid solubility. And you can increase the concentration by a factor of 100 without any change in the fugacity. The fugacity totally stays the same. But now, if you want to concentrate it any further, you need to put some energy in to evaporate that solvent. And to get to that level, you basically have to increase the fugacity. So by the way, when you're working in a lab, oftentimes people are really concerned about concentrated forms of chemicals. And one of the reasons is concentrated forms of chemicals have extremely high fugacities, especially compounds that are really volatile. They really want to escape. They're at very high partial pressure. So as you concentrate compounds down, they become much less stable and much less safe to work with. So as you add energy to evaporate off the solvent, you increase the pressure, but you also increase the concentration. So if you look in nature, you see a very similar thing. You have early steps in the food chain, which appear to just follow bioconcentration. So you're going from the water to a fish, the water to a sardine to a bigger fish. That all seems to follow bioconcentration. But then you get to these top levels, right? You talk about a whale or a hammerhead shark or a white shark, and you get these massive kind of levels of bioconcentration. And the question that Donald McKay poses is, where is the energy coming from when you do this? Anybody want to venture a guess? You're not evaporating off the solvent. Where's the energy coming to go above that level? Remember, you're increasing the fugacity, so you're increasing the pressure. You have to put some energy in. So where do you think the energy is coming from? Entropy. Well, what happens when you eat food? Oh, sorry, I missed it. Kailea, I hope I pronounced that correctly. Do you want to weigh in? Can you explain what you mean?
Well, basically, well, because you have to digest what you eat, so if you're eating something, like, then you go to digest it, like that, your body puts energy into that, right?
Exactly.
So then that gets the extra energy, and then at some point the energy is going to surpass like the amount to change the fugacity.
Yeah, really well said. Sorry, do you just pronounce that Kaylee?
Yeah, it's Kaylee.
That? I'm so sorry, I
That's
apologize.
okay.
As someone who's had their name mispronounced a lot, I can totally relate. Okay, sorry about that, Kaylee. Yeah, I reread it and I'm like, what am I doing? Okay, thank you. So you said that really well. So have you guys ever heard the phrase packing on the pounds, right? Packing on the pounds, right? So when you go to Thanksgiving dinner and you eat too much and you're gonna pack on the pounds. And I like that phrase. And the reason I like that phrase is because it's actually an active process. You don't just passively gain weight, right? You actually eat, and you have to expend some energy to eat, and then more, you get more out of the food than you put in. Unfortunately, I wish eating was used more calories than it took in, but then I could eat a lot more. But oh no, that would be bad, because then it wouldn't be enough to survive. Anyway, never mind. There's a tangent, but just okay. So focus here for a second. Packing on the pounds is an active process, and then what you're actually doing once you swallow the food, and you chew the food, you swallow the food, and then you actively absorb nutrients from the food, and you literally pack away the nutrients. You take it, circulates through your lipids, and your body expends energy pulling things like glucose out of your bloodstream and putting them into specialized cells, which are your adipocytes, to store them for when you need them later. And all of that is energy input. All of that requires some input of energy. And what McKay argues is that these extreme bioaccumulation kind of factors that you see are the combination of the passive forces, right, like biomagnification and bioconcentration, and active energy consuming processes that pull compounds in and pull them out of equilibrium. So a really important take home, if you learn nothing else from my class, learn this idea that these very high bioaccumulation states are not equilibrium states. They're in fact out of equilibrium states where a combination of chemodynamic forces and biological forces act to give you these high accumulation rates. And in the book, or in, excuse me, the reading, in the paper, he basically uses that analogy. He says digestion involves some input of energy to extract nutrients from food and put them into storage. And the analogy he gives is, he says, well, like if you buy food, you go to the store and you go get it, and that's an energy dependent process. So he points out that you can think of it that way. And when we're talking about energy input, in this case, we're really talking about the digestive energy inputs. And that includes enzymes, circulation, storage in fat. And this energy lets you move contaminants out of equilibrium. So what you do is you start with a contaminant that's at or near its equilibrium constant, and you eat enough of it, and you expend energy to pull it out of its equilibrium constant and store it. And so what you're seeing in a whale is basically like a massive disequilibrium state. And one really good way to convince yourself of that is to look at the examples of biotransport, right? So if you take a salmon and you kill it in a stream, right, or it dies in a stream after it spawns, the compounds have such high fugacity that they quickly spread in that stream and go into everything else, right? So you've really pushed compounds out of a state that they really want to be in, and that's one way to understand how bioaccumulation works. So hopefully, in these last two lectures, conceptually, we've gone beyond your sort of high school level understanding of biomagnification and bioconcentration. You have a good sense of some of the forces and constants and sort of oddities involved. Okay, this is our normal sort of stopping point for a little break. Before we do that, so let me just take 1 or 2 minutes to ask, are there any questions?
I was wondering when we'll get more information about the midterm, like structure of the test, that kind of stuff.
So I think we're going to do the same test structure in prior years, where we'll put the test online, and you guys will have a set amount of time to do it. And I think if I recall correctly from last year, you will have a different, I think what's fixed is the amount of time you have to do it. So if you start a little bit earlier or a little bit later, I think you still end up with the same amount of time, but don't quote me on that. I'll double check that from last year. And the test will be a combination of short answer and multiple choice and long answer questions. So you'll have some easier stuff that's kind of more short answer and long answer. And given that we're doing these online, you're doing them on your own, they're open book, so you can use your notes to answer the questions. Yep.
Thank you.
Yeah. Oh, Michael has written to us. Yoon, I don't know if you're still here, but right, Michael's written to us. He still can't see Thursday's lecture on the YouTube link or the Google Drive.
I have not uploaded it onto YouTube. I haven't worked that into my workflow. Sorry about that. I can do that.
Why don't we stick with Canvas? Michael, can you use Canvas? Is that okay for you? It's in the Zoom recordings. Yes. So yeah. So I think there was like overwhelming support for Canvas last time. So rather than having your TA kind of try to do 3 sites, we'll just have them do that. Are we going to go over the assignment? You mean the op-ed? Is that Ashlyn? Yeah, is that the op-ed that you mean by assignment? Ah, okay. So we will go over, my plan to go over the assignment is usually after the first midterm. I see that you guys are real go-getters this year. Like you're really like wanting to get on stuff early, which is good. I applaud that. Generally speaking, most people kind of start that right after the first midterm. So I do devote some time to that after the first midterm. If Ashlyn, you want to start sooner or kind of ready to go on yours, happy to talk to you about it. Or maybe we can take some time. When is the midterm in this class? Does anyone know? I should ask the professor.
I think it's next Thursday.
Next Thursday. Okay. Yeah, I think October 14th. Thank you. So what I would suggest is that like we get through the first unit kind of with the midterm before we start the assignment, just get everybody feeling comfortable with like, you know, what are the tests like? What's the content like? You know, just feeling comfortable with the class. And then we add the assignment in for the second part. So, but Ashlyn, if you want to talk about it sooner, happy to do that. Okay, other questions? Anybody from Huntington Beach in the class? There must be somebody from like Dana Point, Huntington Beach. Anybody from one of the neighborhoods that was affected by the oil? Ellie, I think you're muted, but. San Clemente. Yep. Yeah, so it's just north of that, right? Yeah. Interesting. So it'll be interesting to hear from people who are from those neighborhoods because the tar really sticks around for a long time. I think people are going to be pretty upset with that. Okay, I promised you guys a break. 5 minutes, so 11. Let's reconvene at 11:50. Next, just one last announcement. Next Tuesday, I will do a bit of a whiteboard session. So I'll sort of draw some concepts out and go more slowly over some concepts like octanol water partition coefficient. I'll answer Madhu's question about the exceptional cases. So I'll slow that down for our next iteration. Okay. All right. So 5 minutes. See you at 11:50.